Okay, we are in lab number 12. And you learned many methods, three methods to solve one first order ordinary differential equation. So let's see a example of it. So I'm sure you have done problems like this in your physics or dynamics courses where you throw a particle up and you want to record its position and velocity. So in this case, we have an arrow that we are shooting upward. We are given its mass, 0.11 kg. We are given its initial velocity, 8 meters per second. We are also given when it shoots up, it will slow down due to gravity. And there is also an air resistance which involves a constant K, which is 0.002 kg per meter. So if we model our arrow as a particle, we know that first of all, we will have a force mg downward. And then when the arrow is moving upward, it also has a air resistance force which is proportional to its velocity square. So when the motion is up, we see that if we sum up forces, up being positive, we will have minus mg minus kv square. Now consider when the arrow reaches to the top and starts falling down. Now the motion is downward. And if we draw its free body diagram, we have, of course, the weight force, mg. And now our air resistance would be opposite to the motion, kv square. So when we write the sum of force equation now upward, we still have minus mg, but now our air resistance force changes sign to positive kV square. So to account for this, what we do is we notice that the force always opposes the velocity. So we can write this equation as minus mg minus k times v absolute. So this way, notice when the velocity is positive upward, our force will come out to be negative. And in this case, we will write also the same thing, minus mg minus k absolute v times v. So now when motion is downward, v is negative, this whole force will become positive, which is what we want. So we can therefore simplify our equation, sum of forces upward to be minus mg minus k absolute v times v. And this we know is mass times acceleration, which is dy dt. So our differential equation dy dt will become, if we divide the entire thing by m, minus k over m absolute of v times v. So here is our first order differential equation. This in principle could be a function of t and v, but only involves v in this case. But when we program our Euler method or Runge-Kutta method, we are going to keep our function as function of these two variables. Okay. So our goal is to find velocity using Euler's method, delta t of 0.02, and then we will double it to 0.04 so that we can perform Richardson extrapolation. Now we are going to integrate it up to 8 seconds. According to my calculation, we would have reached terminal velocity, which is constant velocity. So we are going to perform Richardson extrapolation and find out how large our error could be. What is the absolute error bound? And then we are going to repeat this procedure on a separate sheet, solve the ODE again, but this time by Runge-Kutta method. And remember, Euler's method in each step requires one function evaluation, whereas Runge-Kutta requires 4 function evaluations. So in order to make them comparable in terms of computation time, we are going to quadruple 4 times the time step. So we'll make it 0.08 seconds here. Okay, that's the logic. Okay. So you're going to set up a template for Euler, which looks like this. You are going to set up a template for Runge, which looks like this. This is the Runge-Kutta method. So please set it up. And you are going to write 2 functions in a VBA module. So the first function is function TV. This is our differential equation. We just derived it. So we are going to import M, G, and K values from the Euler worksheet. And these would be our cell names, M, G, K. And then this is our first order differential equation. Then we have our Runge-Kutta method. So for Runge-Kutta method, again, we are going to provide it H, the time step, X and Y. Notice X corresponds to time, Y corresponds to velocity in this case, but we keep this generic. So this would be for any problem solving. Now I'm doing a very clever way. So I have set up my K as an array. So I have K1, K2, K3, K4. But notice I've made it a 2-dimensional array so that I can transport it as a vector. So what I do is I calculate K1, K2, K3, K4, and then yi plus 1 is K0. So what it does is I'm going to transfer yi plus 1, which is 0, then K1, K2, K3, K4. So I'm going to transfer back 5 values. So it'll be a row vector of 5 values. This. Okay, so type this in and then we will begin on working on the spreadsheet. Okay, here we go. So we are going to begin with cell names. So let me fire up my Euler sheet. So here is my Euler sheet. So this is the template I wanted you to prepare. And let me also show you, you should have as module 1, you should have these 2 functions. Okay. All right, let's start naming cells. So this is M, this is G, this is K, and this is V0. This is H1, but we can't use H1, so I'm going to use H underscore 1. And this is H2, H underscore 2. Okay, always a good idea. Go, formula, name manager. So we have 6 names. Okay, let's start with formulas. So this is our 2 times H1. Okay, so at time t is equal to 0, V is equal to V0. Also for H is equal to 0.04. Okay, so what we are going to do is we are going to increment our time plus h1. Okay, then Euler's method says take the previous value plus h, which is h1, times function at the previous step, time and velocity. Simple. And we copy these formulas to row 413. Okay, so we get to 8 minutes. Our velocity downward, and you can see it is almost getting constant, nearly constant. Only the fifth digit is changing. Okay. So for h is equal to 0.04, we are going to skip a time step. So we are going to say this is equal to previous value plus h2 times function at previous time and previous velocity. Remember, we need to pick it up from column C. Okay, now we have two values. We'll perform Richardson extrapolation. Remember, local error is proportional to h square. So our weight factor will be 2 square, which is 4. So 4 times thin strip minus thick strip divided by 3. And then our absolute difference between this value and our thin strip value. Okay. So remember, we are skipping a row. So we are going to pick up all these cells and copy them down to 413. All right. And then let's calculate our vector norm of delta V. And find out what is the maximum value is. So it says 0.014. That means we have one correct decimal digit. So let's box it. And folks, we are done. So now we are going to see we use 4 times the time step. That means same number of function evaluations. And we are going to do Runge-Kutta method. You might want to plot it and see what, when you plot column A versus your best value is in column D, and you can see how the error bound works. But we are going to do the same thing in Runge, so I'm going to show you what to plot and so on and so forth. Okay, so let's see what we are doing next. So we have done this, we have found number of CDDs. This is our Euler setup, so you can see my values and check against. All right, let's move on to Runge-Kutta method. So of course, I've got these method inputs, but we are borrowing these constants from Euler sheet. So just for completeness, I have kept it on this worksheet. Plus, you could just copy over, of course, from Euler to this and make minor changes. So here is our H3. So we are going to give this a name, 0.08. Let's give this a name, H3. And we are going to do double it, so that will become our H4. So we are going to give it a formula 2 times H3. Oh, we have not named them as yet. So this is K. Okay, so this is our H3. This is H4. And let's put in our formulas. So we have cell names and we'll start putting in our formulas. So this is 2 times H3. Okay, so initial conditions, T is equal to 0, V is equal to V0. Same thing, V is equal to V0 here. Okay. So we are going to increment our time by H3. And remember our formula, remember this Runge was a vector with 5 values. First value was yi plus 1, and then we had k1, k2, k3, k4. So I'm going to take 5 of these, say equal to Runge. H is H3, X is previous time, and previous velocity. And remember, Control, Shift, Enter. So we'll take in all these formulas and copy them to row 113. And we get to 8 seconds. Okay, so we are done with time step is equal to H3. Okay, so now let's do for next time step. So this was H3, and this is going to be for H4. All right, so we are going to leave a line blank, and we are going to say next time step, Runge H4, previous time is T, and remember our previous velocity, we need to pick it up from column G. Control, Shift, Enter. Now we can do Richardson extrapolation. Our local error, remember, our local error is h to the power 5 or Runge-Kutta method. So our weight factor 2 to the power 5 is 32. So we'll take 32 times this value minus this value and divide by 31. So this is our better velocity value. Then error between this and our thin strip value. Okay, so we are all set. This time, again, remember we are skipping a row, so we are going to copy all this to row 130. Okay, so we are done. Adjust your plots. Let's go ahead and create a plot. Oh, let's summarize this. So we have copied these formulas. Let's go and find the maximum error bound. Okay, so this is maximum of delta V column. Look at that. The error is extremely small, 3 times 10 to the minus 7. And we are showing just actually three digits. We could display many more digits, but that's probably good enough. So now you can calculate how many number of CDDs you have, and I will leave that to you. Okay, so please box it. And we just need to now create a plot. So the next thing what we want to do is, so this is my table. These are my some initial values that you can compare against. And we are going to generate a velocity and absolute error bound plot. So let's take time, x-axis, and we are going to take these last two columns and we are going to insert a plot. Let's move it to a new sheet. So these are our plot. Okay, so first thing we'll move is this to secondary axis. Yeah, I should have moved that to secondary axis. All right, let's do some axis formatting. So let's format that axis. Need to go only up to 8. We don't need so many decimal digits. 0 is good enough. All right, that looks pretty good. Let's adjust this. So let's format this to scientific, and we just need 1 digit. Okay, so looks like this. Let's give these some names. So we are going to select data. Series 1, let's call it velocity. Series 2, absolute error bound. Okay, so now we can take our legend and move it up. Okay, let's also decide, suppose you hide any rows. So we want to make sure first of all we connect data points, and we plot also hidden rows and columns. Okay, we're pretty good shape. Let's do our usual elements. Chart title, velocity, and absolute error bound. Horizontal, time in second. Vertical, velocity in meters per second. There is another secondary vertical, absolute error bound in meters per second. Okay, folks, that's all there is to it. And so Euler, let's move this plot to here. So we have Euler, Runge, plot. So we do file, save as, macro enabled workbook. And this was our video. Okay, folks. So here is some formatting. You can do 4 decimal digits for Euler, delta V for Runge, 1 decimal digit scientific is good. Here is the grading rubric. And please check all your formatting and submit your file.